How do you advance the slides? Oh, okay. These two. Okay, all right, good. All right, I see it. Okay, we'll go on. So first of all, to set the stage, there's a huge quantity of energy inside our planet. And if you look at the information available on the internet, you can calculate that approximately correspond to 20 billion times total energy consumption. If you only scratch a small amount of that, there would be enough clean energy for mankind for millions of years without perturbing the environment on the surface. However, we can't consider this a resource unless we can get at it. And that requires advances in deeper, cheaper drilling, and also in the technology to engineer the heat transfer reservoir down deep that connects to the wells. Right. Deeper is better. The deeper we can get, the better the advantages for mining the geothermal energy. What happens to that? Let's see.
Oh, lost connection. Wi-Fi.
Oh.
You saw that. That's the average.
Maybe.
The Wi-Fi in this room is stable.
Does it have enough bandwidth? Because I have plots on there that are
there.
that are large.
It's even closer yet.
So we should use 25 series. So there's no Wi-Fi connection.
Yeah.
It must be wired.
No,
I mean, it's not Wi-Fi connected, but
get somewhere in two credit on those numbers myself.
well, it's because it's like the
Numbers used to stick to my head slow.
I would not expect it.
All you gotta do is make sure that it's a good solution, you know, and then that average temperature gradient is the key. If we can dig for the average, that means anyone in the world can do it. And I'm at sea as well.
我找到邮件了。
OK。再看。
你有收到吗？
Okay. So if I can get this. Oh, I was trying to start the slideshow. Yeah. But it's hard to see the icon.
At some point.
Yeah,
at some
point. All right. Okay, deeper is better. The average thermal density gradient below the surface is generally taken to be accepted to be 25 degrees per kilometer of depth. And that's an average. There are hot spots like under Iceland, and there are cold spots like under the Kola Peninsula in Russia. But on average for the globe, you can take this number. And if we can get down to about 16-kilometer depth, we're at 400 degrees centigrade, and that's a key temperature because at that temperature, you can heat water to the supercritical point. At the same time, the energy density, as you go deep, increases. A given volume of rock, if you take 1 kilometer volume of rock, near the surface, centered on 2-kilometer depth, that volume of rock holds about 1 gigawatt hour of energy above 20 degrees C. We're not interested in buying energy less than 20 degrees C for our purposes. Okay, so 1 gigawatt or 2 gigawatt of energies in 1 cubic kilometer. If you go down as deep as 20 kilometers, the energy density in the crust increases to 146 gigawatt hours. The 100 increase in energy density. That has implications for simpler heat exchangers engineering. At accessing higher temperatures, we can access it almost anywhere on the planet, near population center, and keep it far away from faults, which could be an issue for seismic activity. And then at high temperature, if we can mine at the supercritical temperature water, we can have high conversion efficiency to electricity, as we do now on the surface with turbine generators. Okay. new technology that I want to talk about makes use of the electromagnetic range in the millimeter wave region, frequency of 30 to 300 gigahertz. That's now used for 5G communications down near 30 gigahertz. You have channels in 5G. It's used in automobile adaptive cruise control radars at 80 gigahertz. And then we use it for many research applications, including fusion energy. This wavelength range is ideal because you can guide a beam in borehole dimensions at a millimeter wavelength efficiently. And the wavelengths are long enough that particulate environment that's generated does not obscure and scatter the beam. Yet the wavelengths are short enough that you can guide it as a beam with a cross section that fits into a borehole. And also it's a good region because we do have megawatt average power millimeter sources with efficiencies much higher than any infrared laser on the average power parameter range. And also we have the technology to guide it efficiently for tens of kilometers. So with a millimeter beam, we could consider a full bore directed energy drilling beam. And we turn the process of making a borehole purely an energy matter interaction. A schematic on the side of that slide shows a waveguide going in the borehole, launching the beam. It hits the target rock surface, raising the temperature to melting and vaporization point, and continues boring down. It's very simple. There are no mechanical drilling mechanisms in there, no hydraulics in the hole. There's no electronics for monitoring. It's just a pure energy matter interaction, grace and simplicity. It's a neat, the title of a book that just came out. The physics of thermodynamics replace all the limits of mechanical grinding. No temperature limits because it operates at thousands of degrees C. Greater depths, lower costs. Faster drilling rates, I'm going to show, would be possible in hard crystalline rocks like basalt and granite. Simultaneous formation of a casing as it drills by melting the rock walls. The current mechanical drilling record for a deep well is 12 kilometers. So we need to exceed that by at least 50%. And this approach has the potential to do that. Okay, first I'm going to go over the analytical basis. And we need to start with how much energy do we need to melt and vaporize rock. The equation I'm showing up there was first published by Maurer in his text in 1968. In the first chapter, he gives that equation for laser drilling. And the first term there, let's see, first we need to melt the rock. So we have to raise the solid rock temperature to the melting point, multiply it by the heat capacity at a solid, then add the heat of fusion, the latent heat to melt it. That requires about 4 to 5 kilojoules per cubic centimeter to melt the salt and granite. Then we need to add to that the heat we need to raise the temperature to the melting point, plus the latent heat of vaporization. This number is not really that well known, but can be estimated, and it's a very high number, higher than melting in rock. So if you add these two terms together, you can arrive at an estimate of how much energy it takes to vaporize the salt and granite, which is about 25, 28 kilojoules per cubic centimeter. That's the starting point. Knowing how much energy we need, then we can calculate how much power requires to vaporize rock. And with an electromagnetic beam, it's only a function of the power you can bring to bear. There's no limit to the mechanics falling off with temperature and pressure. and energy interaction with matter just depends on how much energy you have. So you can extend the scale of power density up to very large values, and the rate of penetration will go up to 100 meter per hour, you can say. It takes more energy intensity to vaporize than to melt, but there will be a limit because atmospheric propagation of an intense electromagnetic beam is limited by the breakdown of the air.
That's dependent on humidity.
Yeah, it will depend on humidity, it'll depend on the dust, it'll depend on the composition of the gas. So there's a breakdown limit. For air, it's generally accepted that about 20 kilowatt per square centimeter is the limit of how intense a beam the atmospheric pressure will hold. So this is what is a problem about at the surface. So as the people that are working on this equation have encountered. And but by the way, this is a limit at surface pressure. The breakdown threshold will go down, will increase with pressure also, and also increase with vacuum too. But this is, since we have to work on the surface initially, this could be taken as a limit, practical limit initially. So if we are limited to that intensity of vaporization, the rate of removing material actually goes at about a meter per hour per kilowatt per square centimeter. Okay, so if we vaporize at 20 kilowatts per square centimeter and keep it going continuously, this may not be a practical assumption because the equipment may not stay up on that long continuously or whatever. But if you did, a 10 kilometer deep borehole could be vaporized in 22 days. That's tremendous. If you look at the deepest hole drilled in the US, the big Bertha Rogers hole in Oklahoma, they went to 9.5 kilometer depth, and that's still the record. I was just checking on the internet. The deepest hole in the US is still this hole that was drilled in 1972-74. They took 18 months to drill. So look at the potential increase that could occur if you could bring that power to bear. The other thing you have to remember is that the power of your source will scale as the square of the hole diameter. A 5-inch diameter will require 1.6 megawatt gyrotron. This is a military source that I'll describe shortly. Target. This is the maximum power tube that has been built and delivered so far. And an 8-inch diameter hole will require a 4 megawatt beam. That would require multiple tubes, maybe 4 tubes combined. You'd have to develop a beam combiner. But this is not unreasonable to think about. The ITER tokamak being built in Carrière, France to achieve ignition has a power plant of 24 megawatt gyrotron tubes to heat that plant with ignition. 24 1 megawatt tubes are being installed there. So we're only talking a fraction of the power that is actually being built now for fusion research. Okay. Also, we need to stabilize the hole if we're going to go to great depths. We have the pressure that we have to deal with as we go below the surface. Here I'm plotting the depth of up to 20 kilometers here. And I'm showing the hydrostatic pressure and the lithostatic pressure that will increase up to a couple of thousand for couple of thousand atmospheres for hydrostatic and over 5,000 atmospheres for lithostatic. Currently they use drilling mud, a column weight of a high density mud to cause a stabilization. but we can't use drilling mud. We have to have an empty hole. So for us, with an empty hole, the barometric pressure scaling depth will apply. And I plot on this curve a column weight of argon gas starting at 150 atmospheric pressure on the surface. That gas, of course, will turn into a superfluid as it goes into the higher pressure range. But the gas law, this state equation holds for superfluids, and you can, as described in this textbook on geothermal chemical thermodynamics. So the same equation is state that holds for the gas holds for a superfluid. In addition, we have another force working for us besides gravity, and that is the temperature. This gas law, by the way, this gas law is what makes diesel engines possible. If you raise the temperature in a confined volume, the pressure will go with temperature. So the pressure will be increased significantly with the potential to go over the lithostatic pressure by relying on this thermodynamic law. The column weight of drilling mud cannot go to the lithostatic pressure or above it. In direct energy drilling at high temperatures, we can exceed it. That gives us another possibility for extraction. Rather than vaporize the rock, maybe we can displace it because we'll have this intense source working internally. For example, if you raise the temperature from, say, 600 degree Kelvin to 3000 Kelvin, you're talking about a factor of 5 if you're fully confined. So you can go 5 times local pressure from 2000 to 10,000. Under tremendous pressure like that, there is a possibility maybe we can displace the melt into the walls and create a casing. If you take all the material and make it into a wall, you can get a ratio of diameter of the hole to the thickness of the wall of about 5. At that value, this parameter, the analytical equations for collapse strength of a pipe say that the collapse strength approaches about fifth or so of the Young's modulus. But Young's modulus of this all gas is 800,000 atmospheres, so only a small fraction of this would exceed the strength of the wall beyond this is that. So we could have stability much greater depths than possible with a mechanical drilling boat. The other thing, how high power mining is possible at great depth, and this is what we're interested in. We want to get to that temperature where it's at the supercritical temperature of water or higher, and we want to get to where the power or the energy density in the crust is very high, so our heat transfer reservoir can be more compact. When we look at the temperature profiles that can be achieved with a pair of boreholes, this is a model where we had 2 boreholes 100 meters apart that go to 14-kilometer depth. This is just a slice at that depth where the average temperature of the crust is about 350 degrees centigrade. And if we look at the gradient, you notice this first heat law, which was put down by Joseph Fourier in 1822, says that the heat flow density is equal to the product of the thermal conductivity of the medium times the temperature gradient. It's negative because heat flows always to the colder material. And if we model the kind of temperature profiles that would occur in the ground using this formula in a finite element modeling code, we can plot temperature contours that will go between the two wells. And we make the assumption that we hold the flowing water at a velocity that keeps the temperature 25 degrees cooler than local. Now, I don't know the details of setting it up, but I can imagine that you could flow a fluid fast enough that the thermal conductivity doesn't heat that fluid to a temperature that equals the adjacent rock. Then when we expand these plots to within 2 centimeters of the wall, we can see what the temperature gradient is at that wall. And the slope of this temperature curve gives us a gradient. It's changing with time. As you mine the heat, the rock is slowly being drained of heat. However, it doesn't occur rapidly. There's about 25% drop in the gradient over a period of 50 years, half a century. So that's a good long time, much longer than enhanced geothermal systems that have been built with fracture reservoirs have shown that it's much shorter. Yeah.
Just a quick question. So you talk about 2 wells at 14 kilometers depth, separated by 100 meters.
Right.
How would you establish flow between the 2 wells?
Well, that's the heat transfer reservoir that will connect. You know, conventional approach now is to fracture the rock with high pressure and make it porous, and then you flow.
Like EGS.
Like EGS, right. But I'm pointing out there may be another approach than fracturing rock here, if we can establish the temperature gradients really high. So at year 0 and 1, we can establish the quantity of flow of 100 watts per square meter. By the way, the thermal conductivity of rock decreases with temperature. Near the surface, granite has a thermal conductivity of about 3 watts per degree, but at 350 degrees, it drops down to about 2 watts per meter per degree C. Like all materials, as its temperature increases, its thermal capacity increases, and the conductivity tends to decrease. So, it is possible. The object of this calculation is to show that it's possible to establish a high energy flow, 100 watt per square centimeter. This is comparable to the 24-hour average solar power on a sunny day, except at depth, we would be doing this on 24/7 time scale. Also, this compares to what the natural surface heat flow is on the surface. It's only 75 milliwatts per square meter because the natural thermal gradient on average, as I showed you, is only 25 degrees per kilometer. So if you calculate the power flow, you're down with milliwatts. This is actually something that I found some of the reporters are asking me about it. How can you power gigawatt power plants with only 75 milliwatts flow per meter squared? They said you could never get enough area to run a power plant. But I point out to them that you're looking at the natural surface flow. We can engineer a thermal gradient that can be as high as or even higher than the average solar power collected by a solar panel averaged over a day.
Is this the area of the drill hole that you're talking about? 100 watts per meter square of drill hole.
Yes, per drill hole.
So you have to drill tremendous areas of drill holes.
Yes, you're right. We would need I'm going to show the amount of area we need. Okay, it will be large, but it will be about 1,000 times less than the surface area of a fractured heat transfer reservoir, where the fluid flows so slowly that it will come close to the temperature of the rock, and the gradient of heat transfer will be very low. So with a heat transfer reservoir based on fracturing, you're going to be inherently limited to something on this order. Whereas if you engineer a geothermal heat transfer reservoir, you can reduce the amount of surface area you need for power by a factor of 1,000.
Just to clarify, you're talking about purely conduction of heat through the rock. That's when you say flow of heat.
Purely conduction, yeah. Like, we're not talking about molten rock in the mantle or anything like that. It's a solid, and it's solid conduction. Okay. Well, these points about geothermal direct energy drilling, we can then make some statements of what's the potential economics of such a hole. So first, the main consumable is electricity to power the biliary beam. In order to properly apply it to cost, we need to take into account the efficiency of the gyrotron source, the transmission line efficiency, and then the melt absorption efficiency, because the melted rock doesn't absorb everything that sits it up, reflects off it. So those efficiencies multiply, come out to about 0.33 efficiency of delivering the power from the wall outlet to the rock surface that you're melting. Okay, taking that efficiency loss, and then assuming a cost for electricity. This is relatively optimistic, but it doesn't include all of the costs in your typical electric bill. This is just the cost without transmission, the cost of electricity. And if we take into account the diameter of the borehole, which tells us how much power we need for a given hole, because it's bigger hole require a lot more power than a smaller hole. This cost plot, cost per meter of drilling versus the diameter of the hole size, is logarithmic in both dimensions here. So the lines look straight, but they actually go up exponentially with the diameter of the hole. If we take 8-inch diameter hole as an example, and we look at the cost to drill that, it comes out to be about $85 per meter of hole to remove that much material using electricity. Okay, so the electricity cost for an 8-meter deep hole is about $700,000. I'm taking 8 meters because I can compare it to a conventional mechanical drill. The holes that go to 10 kilometers are very rare, once in a decade type holes. The Chinese have started drilling a 10-kilometer hole this past July with their goal of 10.5. It's a big deal because it was announced on the news and all. I mean, to get to 10-kilometer depth is a big deal, and you don't really have the cost for that. Those holes can be hundreds or $1 billion cost, but 8 kilometers holes, there's some data. And they cost somewhere over $50 million to drill that deep. So I'm talking about electric costs in comparison to a mechanical hole of about $700,000. Now this includes all the other costs involved, labor and hardware and all this. This is just a consumable, but this is a very small number compared to overall costs, approaching a couple of percent. So there's potential there for lower costs. But then when you add in no drilling mud costs, no casing costs, because it will occur simultaneously, and the much shorter drilling time, instead of 18 months, 1 month, there could be a significant savings. It's beyond me to calculate in detail, but I hazard a educated guess that would be 10 times lower to drill a deep well with a direct energy drill than a mechanical drill. Right. This is the gyrotron. So I talked about millimeter sources. This shows a tube without being inside a magnet built by the Japanese Atomic Energy Agency for the ITER project. It's a 1 megawatt tube at 170 gigahertz. The principle of the gyrotron and why it's so efficient, it starts with an electron beam, which is sent through a resonator cavity inside a magnet high field magnet. And then you have a very efficient interaction at the electron cyclotron resonance that converts the beam power to millimeter wave electromagnetic power. And then as those two beams exit, the beam is separated from the gyrotron, the spectral electron beam, which is collected by a large collector up here. If it's 50% efficient and you're putting a 2 megawatt beam through here, this thing has to collect a megawatt of energy. So it's a big structure. And then the electromagnetic beam is sent out through a window through the side, which has to be a diamond window because in the development of this technology, it's been found this is the only material that will stand a megawatt at a megawatt CW at this frequency. All right, so this shows a tube of 1 megawatt, 110 gigahertz installed in its magnet with a big collector on it, the big oil tank for collecting the high voltage power source to the beam. It's about 90 kilovolts here. And so the GA has 6 of these for their fusion experiment, and there'll be 24 of these for your experiment. Well, we have to guide the beam too, because we generate on the surface. The gyrotron does not go in the borehole. I've had that question asked me a lot. How do you get the gyrotron in the borehole? It does not. We take the beam and we guide it by an efficient waveguide into the borehole. An empty overmolded waveguide, and by overmolded I mean the diameter of the hole is many times the wavelength. So if you have a 2 millimeter wavelength, the waveguide can be 10 centimeters or more in diameter. And we found, actually Bell Labs developed this technology in the 1950s before laser and fiber optics. It's been found that if you corrugate the inside of the metal wall by corrugations that are 1/4 lambda deep, and there are at least 3 or more per wavelength, you could propagate what's called a hybrid mold, HE11 mold. This kind of surface boundary causes the electric field to approach 0 at the wall. And that's why it's so efficient, because there's no electric field at the wall, very little electric losses. It has a Gaussian beam when you launch it. Here I plot the theoretical transmission efficiency for a copper corrugated waveguide at 105 gigahertz, 12 centimeter diameter. It's over 90% to 20 kilometers. That's why Bell Labs was interested in the 1950s to improve communications between regions with high capacity data. They needed something that could transmit tens of kilometers of beam of energy at these high frequencies. Of course, in 1960, the laser was invented, fiber optics. So we have laser fiber optics. But this mode is the same mode that propagates in a hollow fiber optic. It's the most efficient guided mode possible, but only the diameter about 10 to 100 microns. Here we can propagate this mode in dimensions of many inches. Of course, copper may not be practical with a drilling application. Carbon steel, if we use that, that's still over 70% efficient at 20 kilometers. And also granite, as I showed, if granite is open up, it's a dielectric, like a fiber optic, and that itself will efficiently transmit the beam for about 100 meters without any metal waveguide in there. These are commercially available, atomic, they have various sizes you can get. And they supply many of the ones in the fusion research.
What kind of thickness these need to have?
What's that?
The thickness of these guides.
The guides,
the wall thickness.
Well, I think from GA they're probably about a 1/4 inch or so. But the thickness can be whatever you want it after the corrugation. The important thing is the corrugation. We've demonstrated the feasibility here at MIT with experiments at 28 gigahertz. You can buy a commercial gyrotron system, all compact, and built in with the power supply to controls. And here the gyrotron is a small drum on the bottom. It sits inside a copper magnet solenoid. At 28 gigahertz, you don't need such a high magnetic field. It doesn't have to be a superconducting magnet. So it makes the system simpler, and we can launch a beam that goes up vertically and is transmitted by waveguide across the lab to the test chamber. Here, the insides of test chambers are pulled out. It actually all sits in a steel cylinder that's closed to prevent any stray radiation from going out in the lab and being a hazard. So the waveguide inputs a rock. Inside the cylinder, we have a Teflon coil through which we flow water. And in this way, we measure the efficiency of absorption. Remember, I said that the melted rock absorbs 70%. Well, this test chamber with no rock is used as a power meter for the gyrotron. So we measure the power. Then we put the rock into our experiment and make the hole, and we collect 30% of the power in the water. So from this, we calculate that the efficiency of molten rock absorbs 70% of the beam.
And unmelted rock? What's the reflection coefficient?
What's the
unmelted rock? Just the rock.
Unmelted rock. Actually, granite has a lot of silicate in it, which is somewhat transparent. This will transmit about 70% of the beam. But once it melts, the melt becomes much more opaque than the unmelted rock, and it only scatters about 30%. So yeah, there is a difference in how well rock absorbs, whether it's melted or unmelted, and the melt absorbs much more strongly. So we demonstrate all basic elements of a system for drilling. We put reflective power isolation in the waveguide. That's something important. In the fusion program, the plasma is like a black body, it absorbs everything. And the gyrotrons were developed, they have no problem. But when the first time I tried this, the gyrotron would trip off because it doesn't like seeing power reflected. So we put a power reflected isolator in to the system, which worked at this power level, 10 kilowatts. We put forward gas, purge gas flow, because the breakdown threshold of air drops as it gets hot. So in order to prevent breakdown in our lab experiments, we flow laboratory air at high velocity that keeps waveguide cool all the way to the rock surface and prevents breakdown. We have collinear diagnostics. We put monitors of the temperature and the melt displacement on the waveguide. These are instruments that occur at a different millimeter wave frequency, 140 gigahertz or 95 gigahertz, which monitor, like FM radar, that monitor the position, and radiometers that monitor the radiated heat. That's how we know we've achieved over 2,000 degrees centigrade in these experiments, because we measured in real time. The borehole we found guides the beam, like I mentioned, the dielectric cylinder guides the beam, just like a fiber optic. We've observed that, and the pressure rise, the equation of state also is verified. We've observed small pressure rise in our experiment. And this is the result of one of the rocks. This is a laboratory borehole in the basalt rock that's 10 centimeters squared. This is the waveguide where the inside diameter was tapered to launch a focus beam. But it drills a 50 millimeter beam. That's because if the aperture that launches the beam is 20 millimeters, and the wavelength is 10 millimeters, you have a big diffraction. So this beam launches with a divergence angle of 50 degrees. If you look at the cross-section of rock we drilled, it was 38 millimeters of rock, you notice there's no divergence in the rock hole. It's relatively collimated. That's because the hole itself became a waveguide and collimated it and guided it. The military wanted to use this as a weapon. They bought many gyrotrons out in Albuquerque, New Mexico. And it doesn't work because a few meters away, the beam is diverged and it's not lethal anymore. But it turns out the application of a gyrotron in a borehole is ideal because the borehole acts as the guide to keep it at high power for a long distance. And, you know, we did see a 4 millimeter thick wall without pressure behind it. So you can make a glassy vitrified wall. And you'd also notice the thermal stress on the rock. This sample had to be banded by a steel band to keep it from falling apart. The first time I did this in the lab, it was like putting a stick of diamond in granite. After the rock got to temperature, melt temperature, it would blow apart from the stress, and you see all the stress, thermal stresses. So we had to band them in order so we could see the holes rather than pieces of the rock. And we had a lot of pieces of the rock in the test chamber initially. So that's actually it. I just wanted to say that this has been licensed to Quays, the company that spun off to develop this, to commercialize it for mill rig drilling. They want to enable super hot geothermal systems for electric power. And their goal is to actually implement it on abandoned coal plants that are currently exist around the country. Well, you already have the power grid structure at those sites. You already have the electric generators. The only thing you did is you removed the furnace, the coal furnace. And what the goal is we'll just put the replacement by deep geothermal wells and bring up supercritical heat to operate that plant exactly as it was operating before. So the geothermal plant that they're envisioning is already 75% built. You just have to bring this part in to replace the supercritical water. And they have made an advance in the depth of the hole. This is their test. You know, at MIT, we had a diameter or a length of the hole, depth of the hole, to diameter of about 1 to 1. You know, I showed you a 40 millimeter deep hole, 50 millimeter deep hole. But at Quays, they've actually achieved just recently in the past year 100 to 1 ratio. This is deeper than any infrared laser was able to do since the 1960s. Because what happens with the laser experiments, as you transmit the beam with the airflow to remove the particulates interfere with the beam and block it. The deepest hole in 60 years of trying with lasers, only 1 foot. And here Quays was able to do a hole that's already over 6 feet. You know, and actually, I have to say that they cheated here because it takes a long lead time to buy a gyrotron. So they got a surplus klystron from Cambridge University in England that produces about 10 kilowatts, not more power than I have in the lab here. And the grant they had from RPE says the goal is to get to this hole. So they connected up this klystron to a small waveguide. This hole is only 2 centimeters in diameter. It's about half the size of the one we make here at MIT. But they were able to push it in with the waveguide, and they didn't really vaporize the rock. They were able to make it by blowing intense air with the beam, just like the fiber lasers were doing. But they couldn't, because blowing the air with the particulates blocked the beam. But here at a 10 millimeter wavelength, blowing the air and particulates don't block the beam. So they could go all the way through. Notice that it's this heavy steel casing because that issue of it blowing the rock apart unless it does have support around it. Of course, deep underground will be the electrostatic force that will keep this together and allow us to go to at least 16 kilometers, we hope. So, sorry that it took so long, but the summary here is that I hope I showed that the physics are good to go deeper, faster, no temperature limits, in a millimeter wavelength range for doing this. It's the ideal range. It's long enough to not be perturbed by particulates, short enough to be concentrated in high energy. The economics are good, no drilling ones, self-casing, electricity costs minimal, and it will result in the possibility of smaller heat exchangers underground. And the main technology is already here. The powerful gyrotrons exist, efficient waveguides exist, and the laboratory experiments have shown feasibility. So Clays is working harder. They've received the 100 kilowatt gyrotron at 105 gigahertz, and they're fabricating a field unit, and hopefully we'll see some progress. Breakdown is a limit, and then the other thing is, as we get deep to high pressures, because I showed we want to get to thousands of atmospheres, we have to not treat the waveguide's no longer empty. The gas will be a superfluid, and the transmission efficiency of that gas needs to remain small. And so we need data on that to see how deep we will go. But the potential is there. And the reason I showed argon is the less likely to have collisional dipole moments that can absorb the beam. So that, no. We took up the hour, unfortunately. 10 minutes that was setting up the computer. Sure.
Those thermal cracks that you were making, do you think those are during the heating up or the cooling down of the hole?
The what?
The thermal cracks you showed.
Oh, that's well, that's a good question, because I think I've heard it crackling after we turned off the beam too on occasion. But the basalt will break on heating up. It does break as you're doing it in the process. But I have heard granite still crackling after we turn off the power.
I guess those have implications both for the stability of the borehole, but also for the heat transfer in your model. Like if you were creating cracks around your borehole.
Oh yeah, that's a good point. Yeah, that has a good model. I assume the wall has the same thermal conductivity as the rock behind it, and so as we change it with glass, but basalt glass heat conductivity is not that much different from the basalt itself. Ordinary glass does have a very low thermal conductivity. Yeah.
And if there are fluids in the rock, which is
yeah, I was told by the drilling community, well, what about the water in the rock? You know, how is that going to affect you? Well, water has is vaporized very easily. Like some of the rocks we have, like granite, are not completely dry, and they do dry out within the first few seconds, though, because it vaporizes at a low temperature. That goes, and you know, typically the water content might be on the order of 5% or so in these rocks. It's always present, I'm told, but that would be quickly handled. Now, one drilling engineer asked, well, what happens if you hit a lake underwater? Because they drill, and then his colleague says, he goes, you know, that stops the mechanical drill too. You know, yeah, water is absorbed very efficiently by the millimeter range of electromagnetic radiation, and it's used as the medium with which we measure the power of high power beams. We use the absorption of water to measure it. Yeah.
So would you expect your beam to be interacting primarily with the melt or with the rock? And I'm asking in regards to the reflection and absorption efficiency. Like, is it going to be mostly 70% or 30%?
Oh, well, it's going to interact with all the phases of the rock as you heat it. And it'll be more efficiently absorbed in its melt stage. And the reflectivity does change with the state of the rock, because we monitor reflected power, so you can see a little jump in it where it melts, because it becomes more reflective and less absorptive. well, actually, it's becomes more reflective when it's a solid. In the case of granite, it's more transmission into the rock rather than reflection, and the reflection corresponds to the discontinuous change in dielectric constant from air into the medium, and so quartz has a lower dielectric constant. Well, not quartz. What I'm saying is granite in a solid will transmit into the volume of the rock fairly easily. You can have a 3-inch thick piece of granite and you can still detect the beam on the other side when it's solid.
Oh, so that's a good thing. So it's not reflected, it's actually penetrates more deeply.
Yeah,
it still deliver the energy.
That's right. It doesn't reflect as well as a solid, but it transmits and it will go in deeper. When it becomes a melt, it may go in only a few millimeters at most from the surface because it's much more absorptive. But this continuity, what is more evident, because what doesn't get absorbed gets reflected back. Whereas when it's a solid, what doesn't get absorbed gets transmitted. Yeah.
Why millimeter? Is it you defining the wavelengths based on characteristic size of your minerals? Like we know granite is a few hundred micrometer, the mineral size, the crystals on average. Is it like the best efficient way is like, oh, I'm going to send 2 millimeter, EM wave there.
We didn't know in advance why millimeters would be so good. We had the sources, we had the published literature on infrared laser drilling. It didn't work, and it was stated in some of those references that the particulates blocked the beam, and we knew that millimeter waves aren't affected by small particulates, and as long as they're dry. There's an experiment in my lab that I like to show visitors. We have a millimeter wave system using a measurement across the beam. And I'll take a paper towel from the restroom and put it in the beam, and it doesn't affect the signal. It's like it's not there because it goes through the dry particulates of the paper. We didn't do any analysis of granite crystals and structure to determine that they're good. It was actually, we had the source and we tried it, and it seemed to work.
So you mentioned deep boreholes and granite. Will this technology apply to drill holes right from the surface, or would you do conventional drilling up to certain depth?
Yes.
Or how about other type of samples? Have you tried?
Yeah, that's a good example.
Like sedimentary rocks or like carbonate rocks. Have you tried those in the lab?
What kind of rocks?
Carbonates, like limestone and sandstone.
We haven't tried it, but your first part of your question about hybrid drilling, go with mechanical drill and then go with the gyrotron. That's definitely something that's being looked at. The mechanical drills are very efficient near the surface, 1 or 2 kilometers. And there are a lot of dry wells around there in Texas. And we're talking about, well, why don't we then send in a gyrotron beam in a well that already exists? And there's a lot of talk about that. One of the stumbling blocks is a gyrotron beam, electron beam likes to have a very straight path. If you put bends and kinks into it, there are losses these days for gyrotron beam. And mechanical drilling well holes are not straight. A lot of them are corkscrew, like Quays has been meeting with engineers about existing holes, and we're looking at that. And calculations can be done about the beam mode conversion, negotiating the bends and twists in a mechanical drill. But that would be the ideal thing, is to use an existing hole and then continue on where the mechanical drill stopped working or became too expensive. So it is a possibility. And then carbon rock, we've tried a number of rocks, melting rocks, sandstones, limestones in the lab. Generally, the hard crystalline rocks melt easier and faster. The sedimentary rocks are more difficult. And it also goes a little bit with the silica content in the rock. The viscosity of a melted granite rock is very poor. The viscosity of a basalt, it pours like heavy oil or a thin oil. So there are differences in rock. And the harder it is, it seems, the easier it is to melt. Yeah. So I suspect the carbon rock would melt. Because look, we're raising the temperatures to 3,000 degrees. You know, at that temperature, there aren't many materials that can stand up to that. And the temperature is not a limit. It's only once it starts pouring, like I noticed in my experiments, once the melt starts pouring away, the temperature drops because the hot, low viscosity stuff leaks away first. If I don't make a hole and the pool stays there, we heat it, we could get up toward 3,000 degrees. But once the melt starts flowing away, all the low viscosity melt goes away and the temperature drops. But we're not limited by how high temperature we can go because we can continue exposing the power. I mean, the gyrotron is heating the fusion plasma to 100 million degrees centigrade. Okay. Yeah. So
I have a question.
Yeah.
Line here. Hi.
Yeah.
Early on, you showed a slide with kind of a vertical section through the device in the borehole, and I understand you said the gyrotron won't be in the borehole, but you talked about the gas purging. And that's what I'm most interested in. I think in the picture you showed early on, there was sort of a central injection of, I assume, some kind of purging gas, and then the vaporized rock would go out the sides.
Yes. Yes.
Yeah, so I'm kind of concerned that very hot vaporized rock on its way out might be damaging some of the apparatus, or might be a problem when it emerges from the hole. How much have you looked into those kind of concerns about how hot that vaporized rock is, what it'll do to your apparatus in the vicinity, what it'll do to the atmosphere, sort of environmental things, but mainly the operation.
Mainly the what?
The operation of you know, that you modeled that hot vaporized rock will actually get out without destroying any parts of the device, or, you know, creating any kind of accumulation or accretion around the borehole.
Yeah, that's a good question, and the engineers are concerned about possibility of that. We do plan to purge air at a fairly high volume and velocity, like in the lab. We've never had any damage of our aperture waveguides, which is within an inch of the hot melting rock, which I thought would be a problem, but it could be we're just short holes, and copper is a good conductor, and there's a water cooling jacket not too far above from where the launch aperture is. I've never seen any damage on our waveguide. And by the way, that 2-meter hole rock that Quave's made, they didn't move the waveguide because the mechanics of moving the waveguide straight are challenging. So what they did is they had that big column of rock, and it was on an elevator platform, and it came up as the hole got deeper in the waveguide. And that waveguide, by the way, wasn't extended into that rock about 90% of the distance of that hole. And so it was exposed to all that hot stuff. Now, they did not get to the temperatures of vaporized rock. In that experiment, they were only a little above the melting point, and the debris came out not as a vapor or as a melt. It came out as a sintered a cloud of particulates being blown out, like hundreds of microns in size, that you can see, and also the melt formed threads, needle threads, which I saw in the lab too, as you're blasting the melt at high velocity, it stretches out, and then on the filters and the exhaust, you pick up what looks like cotton candy.
Yeah.
It's not all there's some particulates, but there's also this fuzzy, stringy, hair-like structure.
I think you need to model like the mass transport and the condensation.
Yeah.
They happen.
Yeah. Those are good points, and they are of worry, because I know when they were setting up this experiment, they're worried about the survivability of the wave path. Yeah.
Thank you. Very interesting, very encouraging.
Yeah. Okay.
So just a quick clarification. So for the 10 kilometers deep well, how would you envision waveguide to go down? Is it going to be going down to that depth?
Yeah, the waveguide will be advanced and go down. The engineering of that, of what it actually used, hasn't all been worked out. I'm not sure what Quay's looking at their field.
And that waveguide is connected all the way to the surface?
Yes.
So basically you're having a 10 kilometers long pipe?
Yes, in principle, yeah. Yeah, it would be a heavy waveguide.
That's what I was asking about the thickness, because the weight of it.
Yeah. No, there's other engineers that have brought that up of how do you support such a long column of pipe, because the strength of steel or other materials isn't, if you put 10 kilometers of pipe, the strength of a pipe isn't actually strong enough to support that kind of weight. There has been one fellow that worked out a spider arrangement, and he that would be attached if it went down, that would brace it to the wall in places. So and also looking at what materials. Titanium is the strongest and lightest material, and so there are proposals. Well, why do we make we've got titanium? However, titanium is a poor conductor, but then another person said we can plate it with copper. So there is some engineering of how practically to send such a long column of metal down. You're right. If we get to 10 kilometers, that would be a problem they would enjoy to solve, because
when the pipe is turning, is there, like when there's loss, does some of that heat up the pipe itself?
The bending and twists would be losses, yes. Any deviation from straightness of any significance would cause mode conversion, and then down from that point, maybe a few meters, there'll be a hot spot as that mode doesn't propagate, that mode converter doesn't propagate efficiently. So that would be an issue. And in GA, they were doing some modeling on corkscrew boreholes and whatever. There are tricks that you can use, because mode conversion depends on a beat wavelength between modes. And one of the guys pointed out, oh, well, if that corkscrew has a certain period, then those losses would cancel out. So there's a lot of modeling needed to do still, how to handle imperfections. Yeah.
But the thickness of the metal part probably doesn't need to be a lot, right? What's this?
It doesn't have to be a lot, but it has to withstand the environment, and it will get hot, so you can't make it too thin.
I mean, the pipe has to be hot, otherwise you'll have condensation of the rock vapor on.
Well, we hope we could quench it, the particulates rather quickly, if we bring in a sufficient amount of cool gas flow and quench the vapor within a meter or so. Then we'd be blowing up a cooler mass of smoke. You know, one thing I was looking at is how do they make nanoparticles and how are they formed? And one reference I looked into, burn up of heavy meteorites in the atmosphere. There were studies done that a meteorite that completely burns up in the air, makes a cloud of nanoparticles with the average size of 6 nanometers, very small particulates. So if you have a large volume of air that quenches a vaporizing metallic rock, you can make very small nanoparticles. Then they can be blown out very easily.
Right.
And if the air is a sufficient volume, the temperature would be quenched fairly quickly. So we can't support a melt temperature all the way up the column. There's no way that you could do that. The hot area is going to be active working surface, and within that region, let's say within 10 meters of that surface. And up the column, it's got to be much cooler than the melting point of the rock. Otherwise, like you say, it could do damage, but I don't think the temperature of the extracted particulates can be maintained for long distance.
Yeah, then you have to have a really high airflow.
Yeah.
Do a back of the envelope calculation for the flow to keep it cool.
Yeah. Yeah, in the lab, I needed 1,000 cubic feet per hour flow. I mean, you could feel the flow out of the end of the waveguide before the beam was turned on. That's one of the advantage. Laser drilling tried to do high energy flow to minimize the particulates, but it would cool the surface as fast as the beam could heat the surface. But in the millimeter wave, we found that the surface is not cooled, or the surface may be cooled a little, but the main action of absorption occurs a millimeter or so below the surface. A beam of a few millimeters actually penetrates in, has a skin depth, and you can blow it very forcefully with cold blow of air, but it doesn't cool the gyrotron beam acting on the rock, because what I think is happening, that there's a thin skin that's occurring that protects the absorption in the rock. At the same time, the flow is coming and removing the rock.
That could be.
Does that depth, that skin depth depend on just the power or also the wavelength?
Well, I don't have information on the skin depth, but it would depend on the wavelengths, because the longer wavelengths will be penetrating, I believe. Yeah. The 10 micron infrared wavelengths don't penetrate, so there isn't any skin. And I'm not saying there is a skin. I did some modeling in the finite element code of temperature profiles with the airflow and the beam, and it came out where the curve in temperature would peak like a millimeter below the surface where the interaction was occurring. And then when I did the measurement, there was one remarkable observation I made, is that power is reflected from the melt rock at the millimeter range, which we measure. But also we measure the temperature of the rock by radiometer, which peaks around 1 micron wavelength. The black body radiation peaks by the radiometer. When I was doing the power balance between the measured temperature and then the measured absorption, and I used Stefan Boltzmann law for radiant power loss, knowing the diameter, the temperature. I measured, if I didn't assume an emissivity in the infrared, I assumed that I was radiating 8 kilowatts of power, yet I knew I was only transmitting 4. And so how could my temperature, which works at a higher, which radiates in the 1 micron range, have a higher emissivity? I had to put an emissivity of 0.5 for the infrared radiation and 0.7 for the millimeter wave. But how do you explain that? Because the infrared beam isn't as transparent or as reflective, yet in order to balance the power I'm measuring by black body emission in the infrared to the power beam sort of millimeter wave, I had to give the emissivity of the infrared beam lower, 0.5, and the millimeter is 0.7. And that doesn't make any sense unless there was a thin film which blocks the infrared, a little bit cooler. And the millimeter sees below that little skin. And then it makes sense. So that's how I surmise there's a little bit of a skin that affects the power balance between radiant loss and millimeter waves. But we need more study to confirm that.
Any more questions?
I guess an observation. I'm seeing. My name is Paul Ritchie. I work for facilities, and our interest is an MIT initiative to be zero carbon by 2050. Assuming this is online in 25 years, we have some potential, but this is always a difficult thing, right? My observation is that I don't think I'm discouraged by the length of time it looks like it's going to take for this to proliferate the market, really, because standard drilling technology, and this is strictly from the geothermal energy use standpoint, not the drilling, which since you're billing it as geothermal energy, I think it's a worthwhile thing to say, that there's going to be a transitory technology that we're going to go through before we are able to do what you're doing. And what that is standard drilling technology is going to get to a lesser depth. We're going to take lesser BTUs per square meter out of the earth, but we're going to not boil the water to make steam. We're going to take the BTUs out of a flowing loop, and we're going to use refrigerant as a secondary source at the surface. We're going to use the BTUs to flash the refrigerant to run the turbine to generate the electricity. It's already being done. And it's very, I've been in the market, you've been in the market long enough to see how efficiencies have increased. And then we got to 1 and then COP came onto the scene, and now COP is growing from 1 to, maybe as high as 4, 5, 6. And we thought that with geothermal heat pumping, we might get, with some geosynchronous kind of a heat pump, we might get as high as a COP of 10. But the bottom line is the more energy you put in from this, the Earth's energy sink, the COP will continue to increase. So that's what I envision seeing. I see a steady increase in our COP, which really the sky's the limit once.
What's COP?
COP is the coefficient of thermal performance, which is what we measure the efficiency of the use of electricity to get the heat to where it needs to go. We're charged with heating and cooling the whole campus, really, and our initiative is to do so without creating any greenhouse gases. In other words, really can't burn anything except hydrogen, but you don't want to burn hydrogen anyway. So the idea is that I honestly see that as a bridging technology to get us to the point where we can flash the steam. I also did some calculations on my own, which just were fascinating to me, that if you get a column as deep as 8 miles roughly, I'm guessing, 15 kilometers?
Yeah, well, it's 20 kilometers, about 12 miles.
Yeah, so in that range, what I start to see happen is that because of the density difference in a column of steam coming up the tube and the density of the water going down the tube, it's a driving equation, and it works like any convective system. It's like a convective system in the atmosphere, only it's in the earth and we provide a path for it. It becomes self-driving to a very powerful force. And it's safe too, because to stop that very powerful force of the rising steam, you just simply starve the board or the feed hole. The COP, every time you go deeper, the COP rises. And it gets to the point where it's going to take a lot of time, a lot of industrialization, a lot of efficiency gains. And so I'm still optimistic that we're going to be able to use this technology. That's really why I'm saying it. I think that we definitely need a cheaper way to get deeper. And
I don't think it's going to take 25 years to open.
Yeah, that would be great, because then we'd be able to meet our initiative without going to that transitory stage.
My goal is that we beat fusion energy to power the grid. because we're using a fusion energy developed technology. The gyrotrons were originally invented in the 1960s to heat magnetically confined fusion experiments. And now we have this technology. The thing is, will they be able at Fort Devens develop their tokamak to the point where it can put power on the grid? Or could we take a technology they're using to heat and then use it directly to tap into their heat?
Yeah. It's a funny competition going on, isn't it? I mean,
Yeah.
maybe fusion's going to be generating our electricity before this thermal power does. And if that's the case, then there won't be any need to go deep.
But you won't be able to put a fusion plant here because it's sold
less likely.
It's sold as a power source that has no radioactivity, but that's not true because it takes fuel that's radioactive to burn tritium, which is a nasty thing to work with. They wouldn't be able to locate a fusion plant in a densely populated area.
Yeah, I mean, all you have to do to get that sneaky suspicion that fusion isn't really going to be all that great for us is the fear of people. At the 3 Mile Island plant, every time that show gets aired, nobody wants to touch fission, and fusion is going to be just as scary to the populace, and it's going to be a popular thing.
But it's the
really hard
ultimate
to sell the
source. I mean,
population.
it's the power that powers all the stars. I mean,
Yeah, I mean, it certainly could work, and I'm not a scientist. I love hearing this to see the potential. I love applying the science, and to be able to meet the initiative, it's an exciting proposition. I like the fact Jamie Beard is the one that's selling the idea of using CO2 as a refrigerant.
That's...
And it's like, I'm not so sure. I haven't connected closely with her group, but she tied into getting the oil and gas industry to do this drilling. And I don't think she knows about you yet. I think that I wrote it in an email, but because I don't really know quite how everything, the information moves. If she hasn't met you, maybe she would like to. But she has quite a think tank going there on this whole subject. Yeah.
I'm sure she knows about quiz.
Yeah, that's good.
Yeah.
Okay, well, thanks so much. Can I get a copy of that? It's been requested already.
Sure,
yeah. Okay.